Hello and welcome to the channel. This is part 3 of how to build and code a VFO based on the Arduino platform using an SI5351 clock generator. What we did in the previous videos, we looked at the concept, what parts we needed, we went through the circuit diagram, sort of a bit of a look at how it all worked, and went through how we could put it all together with breadboards and such like. And we downloaded the Arduino IDE and we went through the basics of that, how to get it set up, and then we took a brief look at the code. So part 3, what have we got in store? Well, I thought we'd expand on this a little bit, so hence the delay in this video coming out, because I was waiting for this. So I had actually made up a board. Now there's a lot more on here. This could do a lot more things, but it starts from the basic circuit. This will all fit in there and work exactly as it did on the breadboard. So we literally install these parts and away we go. First of all, we're going to take a look at the new printed circuit board and obviously all the little features and things that I've got on there, and how it all works and how you put it together. These are available. I will supply these. I will go through the details a bit later in the video, but if you want one, they are available. And we'll take a closer look at the code. Now, I've improved the code. I've fixed some bugs in there. There was a couple of little bugs I've managed to fix. Now we've put some more functionality in there. We'll go through that. And also we're going to take a look at using different microcontrollers, because this will also use the ESP32S3, which will plug straight into that board as well. So I've made it so you can use either of those microcontrollers. But we'll look at the benefits of using a more powerful microcontroller and things we can do with it. From the response to the first 2 videos, it was quite clear that a lot of people are going ahead and building this, which I was really impressed with. I thought that was great. And it's a cool project and they are fun to play with. So I went away and I had a good think. I thought, well, let's see if we can make a circuit board. And I thought, well, if we're going to make a board, we need to make it quite dynamic, because there are a lot of applications. Different people want to use VFOs for different applications. So what I've done, I've gone away and I've made this quite feature rich. So let's take a look at some of the features on here. Now, noticeably, this board will take 2 different types of microcontroller. So it will accommodate the Arduino NANO version 3 or an ESP32S3. And this is the development board. We'll talk about these in more detail as we go through the video, but it'll take either of these microcontrollers. The code is different, but again, we'll go through that as we go through the video. We've got our original functionality. As I said before, we just simply install the microcontroller, install the parts that we used in the original video, and this will work straight off the bat. But we've got some extra features in here. Now these are all optional. It's just simply a case of, if we don't want that option, we simply don't populate it. Now all these options are categorized in the parts list, so it's pretty straightforward. If you want certain functions, then it's just a case of populating the parts. Okay, so let's run through the basic setup. Now this is the configuration from the previous videos. So at the top here we have got our clock generator. So that literally connects in at this point here. So the headers, you can literally solder them straight in the board, and the clock generator sits here like so. And if we come down, we've got our OLED displays. And if you remember from the previous videos, I mentioned about the orientation of the power supply to these OLED displays, and it's simply to do with the VCC and ground. Some boards have got these in a different orientation, so I've put both on here. So if you're connecting a board up to here, one of these OLED boards, just pay attention to the ground and VCC orientation. Now we've also got a connection here. This is for the rotary encoder. So we've got V+, which is VCC, ground A and B, and A and B obviously our square waves. And we've got this little header here. This is for a 3-pin header, and it's designed so that we can put a jumper on there. Now the ESP32 runs on 3.3 volts, so it simply means the whole system is a 3.3 volt system when the ESP32 is installed. But unfortunately that is not enough voltage for the rotary encoder, so we've got a choice. So we can actually go to VCC, or we put the jumper over between common and 12 volts. Now 12 volts, you're probably wondering where that's coming from. Well, we'll get to that as we go on through the video. But it just simply means that if we're running ESP32, we can use the rotary encoder. Now we did cover a bit of this in the previous video as well. So you know, these units will take anything from 5 to 24 volts. So the other main features on here from the previous board, we've got our CD4013. This is the CMOS D-type flip-flop IC that will drop straight in there. We've got our two pull-up resistors, R1 and R2, and we've also got our decoupling capacitors here. Now the part numbers, you know, are all exactly the same from the previous schematic. And we've also got this connection here. Now this is for the 7-segment LED display. In fact, it's a multiple array of 7-segment displays. We're going to talk a bit more about this later in this video. And the other things is we've got band down, band up. These are 6mm tactile push switches, and you probably notice I've got VFO and MEM. These are extra things I've added. We'll get to this as we go on, but yeah, there's some quite nice, interesting things we can do with this. We've got a facility here to put a barrel connector on. This is for a power supply. This is a standard 2.1mm barrel connector, and we can supply the board with either 10 to 16 volts DC. We've got various components that are associated with that. We've got a protection diode. We've also got some smoothing with some capacitors here for some filtering, and we've got an optional power in, power out. So you can actually, instead of using the barrel connector, you can put a header on here, and it's just simply a case of supplying the board that way. We've also got facility here for a power switch. So if you were going to put this in an enclosure, it's just simply a case of connecting a switch to this point, and that will switch the unit on and off. Now we've got some on-board regulation. So we've got voltage regulators. So I've got a 7805 here, and that simply supplies the microcontrollers, which in turn feed the supplies to the board. Now there is a bit of a difference here, because obviously the Arduino NANO V3 is a 5 volt system. The ESP32 is a 3.3 volt system, but again it's got an onboard regulator, so we can supply it with 5 volts. The rest of the circuitry actually runs off the supply voltage coming from the microcontroller. So it doesn't matter which microcontroller is installed, the system will run at 5 or 3.3 volts. And there's another voltage regulator here. This is a 7809, which is a 9 volt regulator, and that supplies this header here. So you might think, why do we need 9 volts? Well, I've just put it on there as an option because our mixer, the Analog Devices AD831 Mixer breakout board, needs 9 volts. So I thought, well, if I put that on there, it's a nice little feature, and it keeps it all nice and neat, so you can actually connect your mixer to this point. Okay, so as you can see, I've got the board semi-populated. Now essentially this is the same circuit as we developed in the previous videos, just with the addition I've got some power regulation happening here, and it simply means that we can actually supply this with an external power supply. Now we can actually solder the microcontrollers directly into the board, but I've chosen to use female header. Now this is 0.1 of an inch pitch, which is 2.54 mil, I believe, and you just get it in strips. Well, this is how I do it, and I just cut it down to length. But you can get these, you know, in all ready-made lengths, and then you can put them in. I find it really useful simply because, you know, if you can take the microcontrollers in and out and possibly use them in other projects, and obviously because this one takes two different types, it's nice and easy, so I can just unplug one and plug another one in. And similarly with the Si5351 clock gen breakout board and the OLEDs. Now with these, this is quite straightforward. We could actually fit headers similar to this. What you could do is just, you know, you can get ready-made ribbon cables, or you can make them yourself and just connect them up to the front panel if you put it in an enclosure. Now these headers are incredibly good value. You can get them. I've got a complete kit and a little tool, and I can make my own leads up. Now we've got some ordinary sort of pin header on here. Now that, I don't know if you can see that, but that's the power switch. So all I'm doing is just putting a simple jumper over there, and again we just get that in strips, and we just cut it down to the size we want, and then just solder it in. It's really easy, but it makes for a nice neat job, you know. So now of course you don't have to use this circuit board. I mean, I'm just, you know, I've made it for ease, but it makes life a hell of a lot easier if you've got something structured, you know, and it makes it, you know, reliable as well. So if you're building something, it will be reasonably reliable. Okay, so let's get some power on this. We'll take some voltage tests just to make sure everything's okay, and then we'll fit the microcontrollers and the various other parts. Now I'm supplying this with my bench power supply, which should be around about 13.8 volts. We're getting the right way around. Of course, the meter is set to DC volts. Yep, and I'll keep that on ground. And if I go to this bottom pin here, this is for the Arduino. We're getting 5 volts, and the one from the second from the top on the right hand side for the ESP32, that's 5 volts. And also if we check pin 14 on this unit, yep, we're not getting any power at all, which is correct, because of course the microcontrollers supply the voltage to the rest of the circuitry. So one's a 3.3 volt system, one's a 5 volt system, but the regulation's done on the microcontroller. Okay, so what's left to do, let's just unplug that. Okay, so let's start populating the board. So if we put in our Arduino Nano clone, yep, we can go in. There's the clock generator, and we can put in our OLED. So just make sure we've got the correct one. This goes VCC ground, which is the top one. And that's it. Oh yeah, we need to put in the rotary encoder. Okay, that plugs in there, like so. So it's positive, negative, A and B, and then we'll just plug it in. Bingo, jingo, it's working. Okay, so let's take a look at the schematic. Now I've called this Band Surfer VFO. I had to give it a name, so if you see on the channel any references to Band Surfer VFO, you know that we're referring to this project. So essentially this is the original circuit from the previous video. Well, I say essentially it is. There isn't any difference. I've just added more features on here. Now these features, extra features, aren't dependent on each other. So if you want the feature, you simply populate the parts. Now we'll look at that in a little bit more detail in a second. But if we look here, this is our basic circuit that we developed. Now the main addition is this, which we've got an option to use an ESP32 S3 microcontroller. Now this simply, will drop in, and it simply just mirrors the connections, well, a lot of the connections from the Arduino Nano. Now obviously you don't have to use the circuit board. You can use this schematic and develop your own boards, or do it on prototyping board or such like. So if we look over this side, as before, we've got a parts list. Now I've broken this up into sections. So we've got a basic setup, which is pretty much the same as it was before. We've just got the addition of the ESP32, and instead of having 4 momentary push-to-make switches, we've now got 6, because we've got that VFO and MEM function. We'll take a look at that as well in a second. And if we come down, we've now got options here for onboard power regulation. So it just simply means we can plug in an external power supply and not be dependent on the power from the USB coming from the computer. So it becomes completely standalone. Now within here we've got 2 sections. So the 7805 voltage regulator and the associated parts run the microcontroller. And if we go just down a little bit, you see these ones say optional. Now this is, to put a 9-volt regulator, and as we saw before, it supplies that header. So I'm using it to run a mixer. You may want to feed something else, and it doesn't have to be a 9-volt regulator. It can be, you put 8-volt regulator in here, or 10 volts, or whatever you need. But I thought it was a nice little feature. It's easy to install. And then we get down here, we've got mode and TX sensing. We'll talk a bit more about this in a second, but that's very useful. We've got a signal strength section here, which allows the microcontrollers to read the signal strength coming from the transceiver or receivers, and it can display it, but we can do other things with it as well. And we've got squelch control, so we could get the microcontrollers to control the squelch based on the signal strength level. And we've also got an I2C FRAM module. Now this is really cool, because this will allow you to keep memories. You switch the unit off, switch it back on, it will come back exactly as you left it. So if you've spent time setting the thing up, you switch it off, you switch it back on, you have to do it all again. But not with the FRAM module. It makes it really easy. Now I'm not going to go into any depth on these extra functions. We'll cover these in different videos. I'll just run through them quickly on the schematics so you know what we're looking at. Now, I've just literally labeled them. So this is the signal strength section. This section here is for the I2C FRAM module. But yeah, that works on I2C, so it's pretty straightforward. And we've got squelch control. So this allows us to control squelch on a radio. So we've got control squelch comes from the microcontroller, and this basically goes to the mute circuit in your receiver transceiver. And we've got facility here to fit a potentiometer so that we can adjust the squelch level, and we can display it as well. Over this side we've got the onboard power regulation. So we've got a socket here, a little protection diode. We've got facility for another different alternative power in or out. You can use that as an output if you so wish, if you've got the barrel connector connected. And we've got a facility here for a power switch, and these are our regulators. It's straightforward stuff. Pin 1 is voltage in, pin 2 is ground, and VO, which is voltage out. is pin 3, and depending on what type of regulator you've got in here, this one's 5 volts, that will give us our required voltages. Now obviously the 7805 is to run the microcontrollers, so if you wanted that, you must have that in there if you want to run this off an independent supply. And this is optional if you want. I'll put this in, as I said, for the mixer. So this is a 7809. You can run it that way. So as I say, we'll cover these in separate videos. I don't want to go into any great depth with this. They're nice features. Oh yeah, and we've also got facility here to run a TFT RGB LCD display, which is really interesting. Now this will only work with the SP32, but again we'll get into that a bit later. And also we've got 2 headers here. Now these are simply I2C, and what this allows us to do is in future projects it'll allow the this unit to communicate with other units and either control them or, you know, talk to other microcontrollers and pass information as we've got it programmed in the code. Okay, so what we're going to do now is populate these resistors here. So the 6 2.2Ks and 6 10K resistors. Now what this is for is mode sensing. Now it's important that the microcontrollers know what mode the radios or transceiver is setting, because a lot of radio equipment, depending on the architecture, requires us to shift the local oscillator, generally just by a small amount, just to accommodate the filters. And also we've got the TX here as well, the TX8. Some equipment really does shift the local oscillators when it goes into transmission mode. So I'm going to populate these now, and we'll get it hooked up and we'll take a look at the code. Okay, so let's talk a little bit more in depth about this mode and TX sensing. Now it's quite important that the microcontrollers know what mode the equipment is set in and whether it's in transmit or receive. So what we need to do is pick up a voltage here from inside the equipment. Now maybe you're building your own equipment, but we need to pick up a voltage. Now obviously different equipment, it's a real mixed bag. These voltages could be all over the place. So how we've done this is, if we follow this down, let's take the AM for example, and we come down and we look at this 10K resistor. This in turn connects onto a 2.2K resistor, which then goes down to ground. So this is a potential divider, and what we're tying from this center point here between the 2 resistors, we're tying this into the microcontroller, and this is going into an analog input. Now they're called GPIOs. It's just a general purpose input output pin, but we're going to set them so that they're inputs, and what we're going to do is measure the voltage at the analog pin. So in this case on AM it's going to be A7. Now this is an analog to digital converter, and what this will do within the microcontroller, and we can use this in our code, this will give us a figure. Now obviously microcontrollers, you've got limits to how much voltage you can actually give them. So on the Arduino Nano, the maximum voltage on any GPIO is going to be 5 volts, and on the ESP32 it's going to be 3.3 volts. So I've done a bit of calculation. So what we're saying is we can pick up a voltage here, if it's anything between 5 volts and 16 volts, it will register as being in that mode. So the microcontroller will know that the equipment is in that mode. If we're going to put frequency shifts in there, we can write that around this condition. So let's just take a look at this. So if this is just an online calculator. I thought I'd use this because it's nice and straightforward. Okay, so an easy way to illustrate this is a potential divider calculator. It makes it really easy. This is the formula if you want to work it out, but it's very easy to do it using this calculator. So if we look at a source voltage here, and let's say our maximum voltage is 16 volts, and then we look at R1, and we've got this set to kiloohms, so that's 10 kiloohms, and then we look at R2, which is 2.2 kiloohms, and then we calculate it. That'll give us a voltage of 2.8, well 2.9 volts at 16, and that's at a 16 volt input. And let's take it from the low voltage, let's say 5 volts, and then calculate it. It gives us 0.9, so it's just slightly less of, below a volt. So if we get back to our drawing, these analog inputs will give us a figure between 0 and 5 volts of between 0 and 1024. This is what the information that comes back from the analog to digital converter. So we can use that in the code. So you can have this so that we have got multiple. It doesn't matter on the voltage as long as it's over a certain threshold. Now we've got to be careful we don't switch more than one on at a time on the modes, but yeah, we can just say, well, okay, if it's over a certain figure, then we will register the microcontroller. It will know that it's in AM mode, and then it'll go off and do its stuff. And similarly for the TX8. Okay, so I've soldered the resistors in, and I've also added this header. This is a JST XH series. Everything on here is 0.1 of an inch pitch. I've just basically got a kit. They're not expensive, and it's got various sizes in there, and it comes with the crimps, and you've got the tool as well. Yeah, really useful, makes a really neat job. So I can plug, I've got this lead I've made up, so I can just literally plug that into this header. Now this is the sense pins, so I can connect this up to my power supply and we can test it. So let's have a look at the code. Okay, so this is the code. We've made a revision to it. This is 002. Again, this will be available to download in the description. And if we come down, and as the same as last time, between these bars, this is the user definable area. Now you'll notice there's actually quite a bit more on here, but we'll go through that in a second. We'll look at this mode and TX section. So if we come up to this section, we've got a static ball. Now these are Boolean statements. Well, it's not a statement, it's a variable. So it's one bit, and we just simply say, is it true or is it false? And it's a very easy way of, when you code in, to, it's a decision. So it's true or false, and if it's true, we make it do something. If it's false, we don't. It's as simple as that. So we've got this mode display enabled. So if we change that to true, so let's just do that now. That means that on our display, it's, we're going to be able to see what the mode is based on those wires that are coming off from the circuit board. So if one goes high, then it'll display what mode we're in. And we've got mode shift enabled, so we'll make that true as well. Now what this does is shift the frequency, if we're in a certain mode. So let's say, for example, I was playing around in a previous video with a Cybernet board that has a 3 kilohertz shift on lower sideband. Everything else is at 0, it doesn't shift, but on lower sideband it does, and that's to accommodate the crystal filter so that the lower sideband section will fit through it. So in fact, we actually have to make it minus, so we have to reduce it by 3000. So if we just put a negative on there, that will reduce it, and if we just leave it clear, it will add that to the local oscillator frequency. Okay, I'm going to stop this video here. I had planned to make this a final video, but it was getting too long, so I've broke it up into 2 parts. So in part 4 we will pick up exactly where we left off in part 3, and at the end of part 4 we'll go through all the components, the details and the parts and where to buy them, as we did in previous videos.